Good morning, everyone, and welcome to today's webinar on understanding the design of RC members using ETABS. In this session, we will explore the fundamentals of designing reinforced concrete members in ETABS, understand the workflow, and look at practical aspects and that help produce safe and efficient structural designs. I hope this session is informative and useful for your engineering practice. Let's get started. So the objective of this presentation is to give the background of the design provisions of the codes IS456 and IS13920 applicable for the members such as beams, columns, and shear walls. So I want to make few things clearer regarding the aspects of modeling, analysis, and design. Now, as you all know, we create the model and assign the loads. So we'll be using the load patterns at the modeling stage, where we could define member loads directly on the members like beam loads, slab loads, right? And lateral loads in automated fashion. So all of these are covered under the load patterns, right? Once these load patterns are defined and used, program can recognize as we define the type as well, like the dead load, live load, seismic wind, etc. And that information can be passed on to the analysis load cases. So the load patterns will have a load case automatically defined whenever you define a load pattern. And then this load cases will recognize the type as well. Once we perform the analysis, we'll get the results for each load case. So we have the load case results, and then we'll combine these load case results with appropriate load factors as per the code under the load combinations, whether it is for strength or serviceability. So the design module is a post-processing thing and will recognize all such information, which I will show in the next slide for the design. So these two informations will be passed on from the analysis to the design module. So when it is generating load combinations, spectrum load cases, when present, program will generate 8 sub-combinations for each load combination you define, right? And the envelope of the force will be used, and you can see the permutations of these loads, that is axial and biaxial moments, by changing the signs. And then if you have performed the P delta analysis, that is using the define menu P delta options, once you enable and set the loads for the P delta case, the design module recognizes it automatically internally. And for the column design, it sets the K effective value as 1 internally. When a P delta is not done, the program will calculate the effect length factors as per the code. So these are the only two information will be passed on to the design module. Our recommendation on P delta analysis is that you perform a P delta analysis always, instead of relying on an indirect way of calculating the second order moments in the design through the effect length factors. Program can very well capable of capturing this as you define a p-delta analysis. Right. So once the design is performed, the output is available in various ways. One is the GUI, the graphical user interface, which will give you a ready envelope, a final envelope that can be used in detailing. And tables as summary and envelope. And then again, a report as summary and envelope. The report can be used for submission purposes. Tables can be used to review any particular session location output. For example, if you have a large span of a beam which is being designed, then there will be several outputs, which we'll discuss shortly. And to go through that, session-based information, you can use the tables. So there are two terms you'll be using, and you'll be finding this under the tables and reports, which is summary and then envelope. The summary is at a particular cross section. Effectively, it is also an envelope for that particular cross section from all design combinations used. It should be noted that the program and our recommendation is to design for all combinations, not as an envelope of forces. So we will have a design output from all combinations, and the summary is going to give you that envelope for a particular station location. And there is an envelope output for the whole member. This is at the member level. Then you have this information. So let us discuss the design of beam and the outputs. Just to give you a brief background, our program uses in the design procedure. This is in detail explained in our design manuals, but a brief background I would like to share here. So for the flexure design, the program uses a parabolic stress diagram and along with other assumptions from the code. So when a frame section is a rectangular section, you can see this stress and strain diagrams, and then you have a T section. That is also possible. If you define a T section as a beam, then a T section design will be done based on this strain diagrams. The flexure also involves torsion if present. So the ME1 and ME2 will be designed, and the equation to convert the equivalent moment of the torsion is also done automatically. So the other one related to the beam design would be the pattern live load. The program performs an approximate conservative pattern live load. Because pattern live load is a complex analysis, we have to do it on the floor slabs on each panels, arrangements, etc. So that is also possible within the program, but you will have to take control on those arrangements, and it can also be an automated fashion. Program can handle it. But as far as a simple design is concerned, the program internally does this conservative and approximate pattern live load. The arrangement, which can cause a larger mid-span moment, you can see. whenever a combination is of dead and live, it gives an output, for example, decon S2, and it will have a suffix of 1 and 2. 1 is without pattern live load, and this 2 is with pattern live load. And you can see the second case, it is giving a larger midspan moment, and this will be used in the design. So whenever you see analysis force output of a beam and the design force for the same beam, it could be different because of these reasons. Now let us quickly go through the outputs. So when you see for a beam member, now you can see program can also handle the finite element model along with the labeling scheme that will have same label, such as this one is B22 at second floor. So story 2, B22. You'll find story 1 or the first floor story level, and then there will be again B22 till the roof. It will have the same. We will try to maintain this so that you can know that B22 is at that particular location in a plan view of this building. So it will also carry a unique name for identification. So for this beam, the output, the longitudinal reinforcing is the immediate output after the design is performed, and you will see 6 outputs along the length of the beam. There are nothing but top and bottom for the left zone, top and bottom for the middle zone, and top and bottom for the right end zone of this beam. This is the highest envelope. And when you right click on this member, it is going to give you this form, which has the access to design outputs of all load combinations at various station locations for each combination. And when you right click, immediately it captures to the maximum rebar requirement, which is 710 mm square. You can see here. That will be highlighted. You can also manually select other locations and go to the details, get the information for that particular combination and station location. Before going into the report, so we also have the table output, which you can access via the show tables. So there will be 2, one is summary and another one is envelope. This one is a summary output. And you can see the station locations starting from 150 to 5000. And program by default designs the beam member approximately at every 500 mm along the length of the member to capture the variation of the forces and the design. So if you look at this, decon S8 is the governing combination, and the top rebar required, here it is, 663, right? So I have colored these 3 zones, which is left, middle, and right. I will show that in a graphical form shortly, but you can see the highlighted, yellow highlighted figures are the one which are reported in the graphical output, right? So at 150 mm session location, so you have 20 combinations, and then this one is governing, and that is being displayed here, right? The other output in the table, which would be the envelope output, which is going to give you the end I. There's nothing but the left, and the middle, and the right end J. So quickly, it is giving you the envelope of these 3 and these 5 and then these 3 for top and bottom. And when you right click, and this is the snippet from the report, you're taking out only the relevant portions of it. But what it shows is basically is the design moment arrived with the consideration of torsion and the actual moment. And the required rebar is reported. And by default, all the members are ductile. So most buildings will have the seismic and will be mostly ductile detailed. And in that case, this ductile provisions from 1390 will be utilized. For this case, you can see this is for the 710, and then the bottom is half of the negative, rebar for the negative moment near the support. This is implemented within the program. So the one which you are looking at is very easy to do beam detailing for most cases. So that is a summary for that particular session location, which is the 710. But there is an envelope output, which is going to give you this end, middle, and J end. And this summary envelope output will give you those combinations, governing combinations, and forces. This can be used for the summation purposes for the report. The next is design of beam for shear and torsion. So the torsion is converted into equivalent shear that is done. Plus, it also checks for the plastic shear, which is computed with this sway effects to the left and right, and the maximum plastic shear is computed, and that will be used. And an effective shear force will be computed and will be checked against capacity. And for ductile members, tau CD value will be set to 0 as per the ductile code. And the usual output, which is the shear reinforcement, is reported as a ratio ASV by SV. So you can provide the detailing, the standard set of legends, two-legged, 10 at 200, like that, can easily work out. So in the report, you'll get all those information. And the report is going to give you two rebar output. One is ASV bar S, which is the total equivalent shear reinforcement required for the section, and ASVT by S. This is for shear and torsion. This is the outer hoop two-legged requirement that needs to be satisfied as per the code. Right. So just for clarity, I'm showing it in a graphical format. You can see this. So this ASVT by S is the outer hoop, and then the ASV by S, which is reported for, is the total, whether it is a two-legged or a multi-legged stirrup. So the total is here, and only the outer hoop is reported separately. So while detailing, you'll have to take care of this. Right. So the report structure I already discussed. So to summarize all those, I have put it in a schematic way that you're going to get a top level envelope, which is the I end, middle, and J end, left, middle, and right. So 0.25 L for the end zones and 0.5 L for the middle zone. That can be multiple session locations like this. And then within that, whichever is giving the maximum, that will be reported for the envelope. in each respective zones. Next is the design of columns. So the program uses PMM interaction surface. It generates PMM interaction surface for each column section that you define and the rebar configuration that you specify. So the rebar configuration should be more practical and more somewhat closer to what you're going to detail. May not be exact, but the distribution should reflect your detailing style. So you can control that, and you can see how these stress and strain diagrams are utilized. And then the generation of interaction surface here is based on this rotation of the uh, neutral axis in various. So full 360 is done, and then PMM interaction surface full 3D is generated like this. Next, the program calculates the demand capacity ratio, whether you design or check the capacity for the provided rebar. So both are possible. So in most cases, we'll be designing. Internally, it is going to check the demand capacity ratio, which is nothing but the vector ratio. What is the demand, this OL, and what is the capacity OC, which is from the origin to this surface. And that ratio, when it is less than or equal to 1, it is safe, greater than 1, it is unsafe. And for shear, it checks for both the shears coming from the from the analysis, and the other one from the capacity. So whichever is governing, that will be used. And then the ductile provisions for the column. The program calculates the demand for the beam column capacity ratio check should be 1.4 times the summation of beams for the column capacity. So this is in detail given as an output, which I'll show shortly, but in that it works out the uniaxial bending to work out the capacity for the demand axial force, and that will be used as a capacity. And the enhancement is done to the demand moment, and that will be enhanced, will be shared half above and half below columns. And then the joint shear is also done. Should be noted that this particular design is available only to the station location, which is the topmost location for the column. All right. So graphically, you'll get to see one longitudinal rebar reinforcing, which is showing 1287 for this section, which is top station location, which is 2.55, just at the soffit of the beam. But actually, you can see from this output itself, for decon 20, we have 3 outputs, and whichever is giving the maximum, that will be displayed, and this will be sufficient for most detailing requirement. This output is informative only when you look at the interaction diagram. So you can see the demand capacity ratio of a particular one has been highlighted here, 0.84, and you can see the OC and OL. This dot represents the forces for that particular load combination. You can see several dots in the 3D view. These are all from various other combinations. This is informative, but should be helpful to take decisions where the joint is lying, whether it is on the minor direction or the major direction, and you can update the column accordingly in your iterations of analysis and design. All right. So in the summary report, you'll get to see for a particular session location and a particular combination, what is the rebar required. And it also gives an output to clause 7.1 of 13920, where the axial strength is 0.4 FCK. That is also reported now. And the other outputs, shear, joint shear check, and 1.4 beam column capacity ratio. If the ratio is 1, less than or equal to 1, then it is okay. And other information related to additional moments, if any, calculated and applied. Right. So the other output within the details will be the flexure details, where you can see the calculation of slenderness effects, minimum biaxial moments, and initial moments. All of this are listed here under this table. And accordingly, the design moments will be calculated. So the effective length factors, as far as annexure E, will be computed when P delta is not enabled. So in this case, P delta is done, and this recognition is internal and automatically happens when you enable the P delta options. And when it is done, K internally is set to unity. However, you can see this K sway and non-sway whenever is needed. When P delta is not done, it will be appropriate K values to be used in the design. And based on this, if any additional moment is required, that will also be computed and used. So your final design moment will be based on all of this information. So the shear design, I had already discussed this. The joint shear and beam column capacity ratios. There are separate outputs within the details. You can see the capacity is worked out, and then for the beam column capacity ratios. So you can see the sum of beam capacity moments, both sway to left and right, so clockwise and counterclockwise directions, and the maximum one will be used in the demand. 1.4 times of this. If column above and below both are present, then divided by 2. If it is at the roof level, then it will be divided by 1. So the output table is going to give you like this. It's an envelope, so top and bottom locations. You can pick up a particular column, let's say C7 column, and get, I've taken for story number 2, but you can take the vertical stack completely in a table output, and you can use this to easily detail when you want to vary the reinforcement within the mid height of the story for the column. And then the summary is going to give 3 locations at each section, whichever is governing, and you can see the variations in the combo for each section. So for the column reporting, you're looking at 1 envelope output from out of 3. So the 3 station locations are the base, mid height, and the soffit of the beam. Right. So you can also modify this to put the station location at the top, but typically this is what program does as a default action. Next will be the design of shear wall. So here we have the pier and spandrel labeling and their designs, and an info related to the design. So the design assumes the walls as brace frames. So the effective length factor is set to unity. So as I mentioned in the beginning, we expect the P delta analysis done. That way the second order moments are captured within the analysis. Any additional moment that arises from the slenderness of the section or the member will be captured to the unsupported height in the design. So these are the two important information regarding the shear wall. Now for the shear wall, we have three methods available, the default one being the uniform reinforcing, a very simple one to start with, and another simplified C&T method is available, which will utilize the uniaxial bending forces. So minor direction bending is ignored. So primary forces being the major moment and the axial force. And the moment is converted into compression and tension forces, and the boundary elements or the end zones are designed as short columns. So program can do this method using this method, or whenever you start, you can perform a uniform reinforcing, which is the default section, which is automatically assigned the rebar in this configuration on both faces at uniform spacing, and you will get the numbers. Then you can use the general reinforcing, where you can provide the rebar configuration as required, like the one shown here, by strengthening the end zones. By doing this, the moment capacity will be significantly enhanced for the same section or for the same reinforcement compared to a uniform reinforcing. For these two, the program is going to use the PMM interaction surface. Let us start with the simplified C&T method. Basically, we are dealing with this rectangular section. Let us see, it can also be a dumbbell section like this with different dimensions for the ends, so that those are designed, and then the web portion of this or the internal portion of this wall shall be provided with minimum rebars. And within that, we have design conditions 1, 2, 3. So first condition is program determined edge members. So it automatically calculates the length of this edge members until it satisfies the design of the short column. So condition 2 is you can specify the edge member length and ask the program to design for that. It can be of same or a different cross section here. And then design condition 3 is nothing but the same. It's a hybrid of these two. One edge can also be fixed, other one can be program determined. So this particular C&T can be utilized when you're particularly designing the boundary element. You can utilize this feature after performing a uniform reinforcing. So in the design process or the iterations that it carries out, it increases the length, like half of the thickness of the wall each step, and then till the design is satisfied, it will report this. You can see the left and right edge member and the middle. And for the uniform and general reinforcing method, the PMM interaction surface is generated full 3D. You can see this and how these are generated. And then the reporting will be at two locations, bottom and the top, for a peer label. Right? Typically, the labeling is important. The labeling is done one label per story, like this. Even if you have meshed walls, you can label each of the element with the P1. So program assembles this as a one single peer, and the forces are obtained at two locations only, bottom and the top of that group or a single element. And you're going to get an envelope summary for these two locations. So if you want the variations along the height, then you'll have to mesh the wall and label those elements with different peer labels. Most cases, this should be sufficient. So I'm leaving at that for now. And for the flexure, uniform, and general reinforcing, the program uses 8 reinforcing ratios as shown in this table, the IP min and IP max. So program uses these values like 0.0025 and 0.04 as a default value. So our recommendation is to keep this somewhat lesser like this, this is about 2% range. And within that, you see multiple ratios, 6 ratios within these two and IP min and IP max values. So it'll have several curves like this. The one is shown here for clarity, have all the ratios. So you'll have to do the iteration of the design till the required ratio is bracketed within these two limits. If it is, let's say, 0.03, then shift this IP max should go like 0.04 and IP min to 0.01 or 0.02, right? A similar demand capacity ratios are obtained, and when the OL is greater than OC, then failure is reported in the design outputs. Now, if you go for simplified C&T output, and we'll see these outputs like tension reinforcement and compression reinforcement. I'll show it in another output. So it will be like envelope of this, tension and compression, and whichever is governing that rebar will be reported for the left and the right. And then the shear design, it is common for all. Come to this shortly. And we have the boundary element check, which is going to tell you what is the length of the edge, because boundary elements, as per the code, may not be needed if you're doing the ductile detailing or the special confining stirrups for the entire cross section. So it is something that you have to take care in the detailing. So program only reports how much length is required from in both ends, for the left and right, and obviously for top and bottom. So you can use a larger one and detail it symmetrically as well. And this edge can then be designed using a CNT method or a simple distribution of the rebar required for the from the uniform reinforcing or the general reinforcing as provided. So, so these are the graphical outputs that we're talking about. The left one is the simplified CNT. You can see for the left and the right for the bottom, left and right for the top, how much is the longitudinal rebar area required for this. And you can detail this accordingly. And when it is from the uniform or the general reinforcing, you will see this top and bottom two outputs and one single area required. So, so in this output, the longitudinal rebar is required. Longitudinal rebar required is obtained from a uniform reinforcing. You can see the values here, right? And in this specific output where I shown a double height wall without any connections to it in the intermediate story, that makes the unsupported length equal to 2. So this is the information program obtains from the model directly for calculating additional moments. So you can see the MU2 values reported here are used by the program, and it is obtained from the analysis. You can see the pier forces, axial force, and then the moment from the analysis. It is 18 and 95 only. Let us focus only at the bottom for now. You can see 303, and this is computed. So yeah, I've used a unsupported length factor as 2 because it is 2-story height unsupported wall, and you can see it is the initial plus the additional moment, which is 303. You can see the top is also the same, 299, 299. Right. So when a beam is connected here at the intermediate story level, then the unsupported length factor becomes 1 for this wall. And then the shear design for the wall piers, and the VC is computed based on the ductility type, which we set. Wall ductility type is now available as an override. You can do the override to ordinary or special. So when it is set to ordinary, the IS456 expression will be used, explained in the manual as well, based on the H by L ratio. The tau C value will be used. So this value you'll see changing based on this information you provide. Similar to column, the shear wall output pier design will be top and bottom, and it's giving you the rebar percentages, required rebar percentages. And you should look at the warnings in the table. If any warnings or errors, you can find out why it is easily from the tables. You cannot graphically view all the walls for certain models, and table is the way to go. And then come back to the model, identifying the label and this story, and you can address it in the design overrides as required. So next is Spandrel design. So Spandrel design again is going to be a summary, an envelope summary actually. So for designing for all combinations, and you'll get a single output at 2 locations, on the left and one on the right. So the labeling is the key here. So assume that this is a cell element which is modeled for the coupling beam between the shear walls, and it is labeled as S1. Or even if these are meshed, and then you have applied the S1 label to all of this, and still you're going to get the left and the right end two outputs. When you label them with different Spandrel labels, like let's say there are five, S1, S2, S3, S4, S5, then each one will have left and right. So that will give you the variation within that. But typically, this single Spandrel label is sufficient for most cases where the shear force is significant or dominating the design, the left and right end. Right. Now, if you look at the shear design output, you'll have the regular top reinforcement and bottom reinforcement longitudinal bars. And then the spandrel shear design, you'll have horizontal and vertical like stirrups or shear reinforcement. And then whenever a seismic design, seismic load is involved in the combination, then this becomes a check for diagonal reinforcement. And when required, it is going to give you the A diagonal, which is the total area of rebar required in one strut of the diagonal reinforcement. There is a small typo here in the output, mm square per meter. It is only mm square. This is the total area for one strut. So you typically will have the two X crossing, two struts. And then for each, this is the area you need to provide. All right. And the table output is going to give you the same left and right. And you can look at the warnings and errors, the table when you're looking at multiple spandrel outputs. Thank you. Let me have some questions from the users, so the participants. Yes, that is a question on the modeling. So some situations you're using rigid links to connect a beam to the column to model the eccentricity for other reasons. Then in that case, the information from the beam will not be available to the column. So beam column capacity ratios cannot be computed by the program. There are other ways to handle it, like modeling the offsets for the frames, insertion points. You can try that. When to do a P delta analysis, is there any criteria? Currently, the 1893 code recommends a P delta analysis, but it does not provide uh, a procedure. But the tall building code is giving you that. But in any case, a P delta analysis can always be performed irrespective of the requirement because we are better capturing the second order effects. Can we get the stability index Q values calculated by the ETABS for different stories in a tabular form? Currently, it is not possible. It's an internal calculation done by the program, but it is not available as a tabular output for now. how the PMM interaction curve is generated, even when we choose the option reinforcement to be designed, and we do not specify any reinforcement. No, it requires a minimum rebar, but a default value will be used for the generation. Otherwise, it can throw some errors in the design. We need a reinforcement data, basically, provided by the user. Yeah, the program version I'm using is the latest one, version 23.3.0. The reporting is almost the same for all these versions for several years. Few additions will be there, like zero point 0.4 FCK strength has been added recently. Other than those, rest of them are the same across the versions. There is a query related to C-shaped shear walls. I think that cannot be covered in this session. We will definitely cover this in a future session in detail. Yeah, another similar query related to the peer labeling of multiple legs. I think this requires a separate discussion. We will definitely go for uh, another session discussing the core walls, multi-leg, what is recommended, what is not. All of this will be covered in a future session, definitely. Yeah, is it possible to design the trapezoidal beam? Uh, yeah, I think it is possible using the non-prismatic frame definition. You can design them. Can we add a column as boundary element in shear wall? Yes, you can. You have to take care of that inclusion by assigning the frame with a same peer label. We will share the PPT to this session, maybe in a day or two. There are some special requirements in the modeling aspects, like eccentrical modeling, the connection, and shear walls with multi legs. We need a separate discussion, and we will definitely consider these in. I think I have covered most of those common questions there. I hope the session was helpful for those who are new to, more especially those who are new to the ETABS and trying to understand the design, and for people who also want to know the background of it. Thank you all for joining. Meet you again soon in another session. Bye for now.